So it's recording and the mic is working. Okay. Okay. Good morning. So today is going to be the second lecture on explainability. So last week, what we did was just look at different methods of explainability. What is explainability and going through it. And today we'll expand that definition a little bit more and discuss this from the perspective of, okay, we have explainability. We saw it more as a debugging tool, but now let's look at the actual definition. And we started off by saying it's for human beings. So how is it catered towards human beings is what we are looking at. So that is the categorization of explanation. And after that, we'll be looking at how would we evaluate our explanation? How would we quantify whether explanation is either good or bad and their objective metrics or to do something like that. So let's start off with a little bit of recap by the definition itself. So explanation was essentially the ability of an entity to explain or justify its decisions or predictions in human understandable terms. So we looked at a large portion of this definition last time where we said, okay, given the weights, this is how the weights need to look. If it's not looking like this, then maybe this is not the actual way of for a neural network to work. Or we looked at the last layer and said, this is the Tisney representation where everything is clustered together and this is how it needs to be. Hence, it's working well or otherwise. But there is a something we are assuming at this point when we looked at the explainability last time, which is that everybody who's looking at the explanations basically have an idea of what the explanations are, or they have an idea of the networks themselves. They know what the first layer weights needs to look like. They know what the embeddings in the final layer needs to look like. So that is a very small portion of the human population, right? It's only dependent on the engineers, the people who are creating the neural networks where this is important. But our definition of explainability was very broad. It was for all humans essentially. And when we said that explainability matters, we talked about the idea of trust. And trust is something that humans gain when they use these networks. So it's not about just creating these networks, but using them as well. Hence, we need to cater explanations to this any users who have no knowledge about how a network works, what weights are, what matrix multiplication is, and all these simple things that we just take for granted may not actually be granted for the people who are using these things. So we need to start catering our explanations to them. So the goal for today is actually to expand this definition of explainability to include more of these human beings. And when I talk about these kind of experts or human beings and engineers who know exactly what they're doing with networks, I'm not just talking about like, these engineers in tech companies or something like that. Even people in medical field. Now, they might be experts in their field in diagnosing diseases, but they might not know how a neural network needs to work for them to actually use it. So we have to be able to cater to all these people, to any users as well, whether they're experts, whether they're just common people, doesn't matter. And that is essentially what we are going to be doing. Just going through the recap a little bit more, we had these two large kinds of explainability, which is the intervention based, and another one was a gradient based. Intervention was when we put these boxes on top of the net on the images and said, okay, these are the prediction probabilities and created a heat map out of it. Gradient based explanations were the ones where we use gradients in order to get these kind of reliability maps or saliency maps out of it. GradCam was one example of this gradient based method. So today we'll be looking at these two questions: what constitutes an explanation and what makes some explanation better than others. Now, this is not a new topic. So if I were to go from recap from last time, we actually answered this question, or we at least answered a part of this question. What constitutes an explanation? Well, it can be visualizing weights across different layers. Now, this may be helpful for a few people, may not be helpful for a few people, but either ways, it's basically the explanation that we went with, saying that if you know what the weights need to look like, then you have an explanation as to what a neural network is doing. We had another type of explanation as well, another whatever constitutes an explanation, which is this activation, visualizing activations in the intermediate layers. We kind of tied the activations or the maximally activated neuron back to the patch and said that if this patch is present in an image, then this particular activation, I think this is the most, this one is the brightest one. if some patch exists within the image, this neuron here is going to be activated. That is how we kind of connected one to the other. Again, this requires knowledge of what a neural network is and what's happening within the neural network. We also answered this other question, what makes some explanation better than others? We kind of subjectively visualized it. If you remember last time, what we did is we had three images next to each other, the vanilla backpropagation, deconvolution backpropagation, and guided backpropagation. And we put them together next to each other and said, look at this, one is cleaner than the other, right? So it was an implicit way for us to make this kind of an evaluation. Whether that's good or not is basically what we'll discuss but towards the end of this lecture. But what I'm suggesting here is that we kind of tried to answer this question before. Today, we are just going to formalize everything. So this is basically the summary of last time. I'm not going to go through all of them, of course, right now, but essentially we had slides for everything, visualizing weights, activations, last layer embeddings, nearest neighbor embeddings, dimensionality reduction. We went through all of these, and all of these kind of tried to answer the question of what constitutes visual explanation. The way we'll be dividing this lecture is by saying that the answer to the first question are these types of explanations, and the answer to the last questions are going to be about evaluating different explanations. Now, let's try to answer the first question, which is types of explanations. Even last time, so there are three types of explanations that we'll be going through. Last time itself, we actually looked at two different kinds of explanations. At the time, we did not formalize it. We just looked at everything and said, okay, this is just an explanation, but essentially they were different two types of explanations. Let's actually talk about them separately. The first thing that we are going to discuss is this idea of indirect explanations. So everything that you see on the left-hand side of the screen is essentially indirect explanations. So visualizing the weights, visualizing the activations, maximally activated patches, dimensionality reduction, embeddings, and the nearest neighbors. All of them are what we call as indirect explanations. In this particular case, I think the concept here is important, which is that in indirect explanations, the human beings who are looking at it and who are being explained to have a very good understanding of the neural network itself. Let me jump to the definition so it becomes a little bit clearer. So just the wording of this thing, explanations that visually analyze network parameters and features and indirectly explain the output. So if you were to think back of the elephant example that we had before, which I'll bring about later, you directly saw the image and the overlapping saliency map on top of it to say that, okay, this is the reason why an elephant was predicted. But when you're doing these kind of indirect explanations, which is that you're visualizing the weights, you're visualizing activations, you're not getting a direct reference to an image. Rather, what you're getting is an understanding of the internal neural network embeddings and internal network parameters. By network parameters here, we mean the actual weights and biases and all the calculations that can happen within it. Features, of course, are the activations that are within the neural network. So the human beings that are being catered to by these indirect explanations, it requires human interpreting itself. So in other words, the explanations themselves require an explanation. During last week's lecture, we had to spend a significant amount of time trying to understand what each of them means. For instance, take the visualizing the weights as an example here. Like, we know as human beings that the world around us is made up of very simple shapes, like edges, some kind of simple shapes, and we know that this has to be reflected within the weights. So that basically means that we, as whoever's interpreting these indirect explanations, they have to have an idea of the world around us, and that simple things are basically what needs to be reflected in the weights. Like color, for instance. Yes, there can be infinite color around us, but there's only three. Given R, G, and B, we can combine them in multiple ways in order to get any color. So a neural network has to learn R, G, and B. Right? So we need to see these R, G, and B channels within these kind of weights. It makes sense. So as human beings who are being catered to for these explanations, we need to understand this. So this is where indirect explanations come in. The other kind is direct explanations. The answer is directly out there. Given this kind of an African elephant, we want to know why the network predicted African elephant. We want the saliency patches on top of it. Same thing with feature importance, which was the back propagation, gradient back propagation as well. There's a sailboat here. Sailboat is being what is being activated. Same thing here with the animal as well. Right. So this is more direct explanation. This is one way of thinking about and seeing how different it is from indirect explanations. So to give a formal definition of what direct explanations are, these explanations highlight all regions in an image that lead to a decision, similar to the African elephant, the face of the elephant itself. The constraints here actually are pretty important. No network knowledge is required from the humans interpreting these explanations. So in this case, we don't need to understand the weights. We don't need to understand the activations. We don't need to understand the last layer embeddings, dimensionality reduction techniques, right? So when asking for an explanation, this is just for common people. Anybody who's using an AI system can use this kind of an explanation so as to understand what they are. So no network knowledge is required from the humans. No knowledge about classes or data is also required in this particular case. So a child, you can show a child an elephant figure and say that this is an elephant. And if the child asks why this is an elephant, you can go through and show the explanation and say, okay, this is the heat map where, this is the face of the elephant. And this is essentially why this given an image, this is going to be the elephant. Now, again, so basically you can use these kind of explanations to teach children. What I'm trying to say here is that the person who is being explained to does not need to have any knowledge about either the class or the data. So if I want to make this a little bit more clearer, so no knowledge of elephants in this case is required to interpret this particular heat map. Yes. In this case, you're kind of correct, except that the way we are doing this is if for maximally activated patches, I need to take the maximally activated patches and see that, okay, this is the brightest point at this spot. And I need to know that this particular pixel or this particular activation is associated for a patch. So what I would need to do in that case is I need to select those images within the patch, which has that, sorry, within the images, which has that patch. Right. So essentially, if I have like, let's say 1,000 images in total, there's about 10 images with this particular patch, let's say the face of a person. So, and I need to find those patches, pass it through and see that this is true, that these maximally being activated all the time. So I need two things here. One, I need knowledge about the data itself, which is that I need to know that these patches exist within these 10 images among the 1,000. So that kind of disqualifies the second constraint here. The first constraint is also disqualified because you need to have an understanding about the activations as well. So the way we are dividing this is that for the right-hand side, direct explanation, your network is a complete black box. You don't need to know anything within it. You don't need to know the network parameters, or you don't even need to know the definition of what an activation is. As long as you understand this kind of what this heat map is, you're good to go. That basically is the definition of direct explanation. You're right. Absolutely. So that is definitely one way of thinking about it. But the differentiation here is more from how do you get that thing rather than this one itself. But yes, that's one way of thinking about it. And you can think that it's an easier way of trying to explain what an explanation is. Yes. All right. So these are the two kinds of explanations we saw last time, which is an indirect and a direct. Now, there's a third kind of explanation as well, which is something called a targeted explanation. So to get that, let's actually try to understand or go through the example of the kid from before. So let's say I have a neural network that has already been trained. Doesn't matter what it is, VGG, AlexNet, anything that exists. So there is a spoonbill image. This is an image of a spoonbill. I pass it through the network. It tells me that it's a spoonbill. Now, this is where I want an explanation as to what it is. So if I were a kid and I'm asking why spoonbill, and I know nothing about what the image is, essentially I can say that it's a pink and round body, it has straight beak. So all these features within the image tells me that the image is that of a spoonbill. So the child can now say the network taught me about spoonbills in this particular case. Now this is essentially the, by the way, this image is from GradCam. The method that we saw during last week. So this is essentially what a direct explanation is. Now, let's see a more involved case where we take the last constraint that we had and remove it. The last constraint in the direct explanation was that human beings don't have access to knowledge about the data itself. So a kid doesn't know what a spoonbill was. But then let's take an ornithologist. So this person knows everything there is to know about a spoonbill. So this person is now asking the network, why spoonbill rather than flamingo? Now, these two birds are very related to each other. It's kind of very similar to each other. So the network now has to answer this. It needs to say that the shape of the neck is what differentiates a spoonbill from a flamingo. Flamingo has this kind of an S-shaped neck. Hopefully you've seen it. So, you should be able to picture what that is. But the other one, the spoonbill, does not have an S-shaped neck. The neck is pretty much straight. But the color of the bird is very similar. It's still pink in color, and most other features are same. The contextual cues, where it's like you have water around it, is kind of similar as well. So essentially, what we are now looking at is the differences in the neck. So now the ornithologist can say the network does not know the difference in legs. So the network is only making the decision based on the neck, but then legs are also a little different. Your flamingo has much longer legs than that of spoonbill. In other words, what is happening here is instead of just explaining the decision of spoonbill, now the ornithologist, who's an expert in the field, can actually go through and assess the network and say that this network, yes, it's making the right decision, but it doesn't know the full picture. It doesn't know the whole story, which is that it's not just the neck that is different, it's the legs as well. Some other thing like a fox can say, okay, why spoonbill rather than a fox? Then a network needs to say, okay, everything is different. The neck, beak, body, legs, everything now has to be highlighted before. So, so as to garner trust, this has to be made. This basically gives us this idea of targeted explanation. The target is towards the human beings. The person who's asking the question is who is being targeted in these kind of explanations. So to give a formal definition, explanations that highlight contextually relevant regions in an image. No network knowledge is required from the humans interpreting these explanations. So the first part of it is the same as direct explanations. So it directly highlights difference here is, of course, the contextually relevant regions. And the context is given by the question itself. No network knowledge is required from the humans. In other words, you don't need to know what weights are. You don't need to know what activations are. You just ask the question of why it's this rather than this, or what if something, and you get some highlight back. But in order to frame the question, you need to have some knowledge about the classes or data as required from the human seeking explanations. In other words, as an ornithologist, I need to know that there is a difference between spoonbill and flamingo, and these are fine-grained differences, and we need to able to, and a network needs to be able to show us what these differences are. This essentially is a targeted explanation. Any questions about this?
We have trained the network with different data. Like suppose we are using probably words and some other things. So that's why it's generating that
Mhm.
maybe in the second one we are training the model with training those versus these four.
Not really. So it's all based on the same network. It's what we backpropagated. So I'll come to that in a little bit. The method in which we have gotten each of these saliency maps. Basically, we are backpropagating different thing. In GradCam, we were backpropagating the logit for spoonbill. Here we'll be backpropagating loss between spoonbill and flamingo, but it has still been trained on the 1,000 classes of ImageNet essentially. Yeah. So essentially, targeted questions can be three forms of questions. One is why P, where let's say P is a prediction. Then what if counterfactual. And the next one is why P rather than Q, which is a contrastive. I think the next image here is going to be easier to explain what all of them are. So given this image, this is actually a very popular image of, if you see any explanation paper, this is one of the images that they're going to show. This also is from ImageNet dataset. Network, or the ground truth for this is that of a bull mastiff. So a network needs to predict that this is a bull mastiff for its accuracy to be high. Now, if you ask the question of why bull mastiff, this is what GradCam gives us. the face of the dog is what is important. If you are asking a counterfactual question, and counterfactual question is essentially any question of the form, what if? It needs to start with what if. So if you're asking what if bull mastiff was not in an image, what would the network have done? Well, it would have made a guess, or it would have made a prediction based on this part of the image, which is that of a cat, which kind of makes sense. Next one is why bull mastiff rather than a boxer, which is the contrastive question. Boxer is the most related to a bull mastiff, and you can say, okay, the jowls of the dog is what makes them different, makes a bull mastiff different from that of a boxer. And of course, the presence of a cat is going to make sure that it's not a boxer as well. So these are the three different kinds of explanatory paradigms that we can think of in terms of targeted questions, sorry, in terms of targeted explanations. It can be a correlation, the observed correlation-based explanation, observed counterfactual-based explanation, and an observed contrastive-based explanation. Yes. In this particular case, it's actually based on the method. So this is an actual thing that is a method that is given. So these are spurious correlations that exist between a bull mastiff and a cat in this particular case. So given this particular image, you have about 70% of this, I'm making up the numbers, but you have a high percentage is that it's a bull mastiff. There's a much lower percentage that it's a cat, and it's a much, much lower percentage why it's a boxer. So what we are looking at is a difference between the higher percentage of bull mastiff and a much lower percentage of the boxer, but we're not changing anything with the cat itself. So it's an artifact of the method rather than just an answer to the question, if that makes sense. Yeah, it's an I wouldn't say it's not an answer. I would say it's more of an artifact within the way the method is generating. Like if I were to go back to this kind of question here, so this is very red, which means that the difference is in the neck, but there is something that exists here as well. Ideally, this should not have been there because it kind of is overlapping, right? Because the existence of this should not preclude the spoonbill. So I would say it's a problem with the method rather than the idea of what the method is giving us. Sure. Yeah. 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 I agree. Yeah. Yeah. Sure. Exactly. Yes. I'll talk about what you said in a little bit when I show more results. So it's about how the a well-trained, what is the definition of a well-trained network and how it's doing. In actuality, you're not even supposed to get these kind of differences. If a neural network knows that these are the causal pixels, why it was a bull mastiff, it doesn't need to know the answer to why bull mastiff rather than boxer are still those causal pixels that exist over there. So technically, for a completely well-trained causal network, you're not supposed to get any of these answers. But the fact that it exists is a reason as to okay, the network is doing well or not well, and it gives you a measure of trust, basically. So this, as an aside, so we basically have a paper on this, which was a magazine paper on this, which talks about what all these different kinds of questions are and what exactly these paradigms are showing us. And if you want to think about it, the way you can use these further on, basically, to a different kind of a reasoning mechanism. We usually think of deductive and inductive reasoning within neural networks. That is basically how reasoning happens. But there's another method, another type of reasoning, which is abductive reasoning. And these three questions are basically what gives us an abductive reasoning framework, essentially. So let's go through the actual method of getting these explanations. So we started off by doing GradCam last time, which is an answer to YP. In fact, many of the intervention-based saliency as well was an answer to the YP question. But we're just going to take GradCam and see how we can use GradCam in order to get the counterfactual and contrastive explanations. So the way, just a recap about how we did GradCam, we passed it through a neural network. The layer that is important to us is the last convolution layer. We pass it through the last convolution layer, pass it through the fully connected layers, and get the logits. Given the logit of whichever one, let's say boxer in this particular case, I'm going to back propagate this boxer. I think this should have been bull mastiff actually. Given this bull mastiff, we back propagate through the network, and we once we go to the last fully connected layer, last final convolution layer, we do this kind of global average pooling on the gradients. And the definition of global average pooling is basically given every kernel within the network. Let's say there are 64 kernels of size 7 cross 7. I'm just going to take the 7 cross 7, bring it down to just a single number. I'm going to take the average of that and make it into a single number. And I'm going to call that as an important score, essentially. So this is the gradients of the logit YC based on the activations from the final layer. Given this alpha KC, I'm going to multiply it against the channel. Now, going back to the previous example, if we had 64 channels of 7 cross 7, which are now our activations, I have 64 numbers, which is the important scores from gradients. I'm going to multiply each of the kernels with it. And that basically is the linear combination here, alpha K into AK. Now, I have 64 different channels. I'm going to collapse it into a single one by taking the average. That basically is the sum that you see here. And then you have ReLU. So anything that is negative is going to be made 0. That basically is our map, and we get the heat map based on that. We now increase the size back to the dimensionality of the image itself, and this is what it is going to look like. So this was GradCam that we did before. Now, all direct explanations basically are answering this kind of a YP question. So again, GradCam does it. Same thing with interventions based on saliency and all these other things as well that we saw, guided back propagation, all of them that we saw last time. Now we can ask some other question as well. We can ask something like why blue jay? It's not just, we are not just limited to the logit that we are looking at, which is bull mastiff in this case. We can ask any kind of a question. We just need to know what the index of blue jay is going to be. I don't know what the index of blue jay specifically is. Let's just say it's 900 among the 1,000 classes. So I'm taking the 900th logit, back propagating it through the network, and I'm getting some kind of a result on it. And I'll get some, I'll do the exact same thing before, except before it was YC that we were back propagating. Instead, now we are back propagating some other class, in this case, blue jay, YI. And we'll do the exact same procedure and we'll get this kind of a result. Now, most probably what you're going to see is the same result as the original result that we had with bull mastiff is what you're going to see with blue jay as well. The reason being that the probability that a neural network predicts for blue jay is almost 0. And it's just basically trying to get the most important pixels that lead to this kind of a very, very, very small probability prediction. And most probably it is going to be the regions that is being used to make the prediction that it is a bull mastiff as well. So this kind of reduces the trust that you have within the neural network, because you're not looking at the actual blue jay at all. Like, this is not showing the actual blue jay at all. And this is where these kind of contrastive explanations can in fact help. Now, before going to contrastive, I think let's just look at counterfactual explanations. So the difference between counterfactual and GradCam explanations is that instead of backpropagating the gradients directly, we backpropagate the negative of gradients to obtain alpha C. So in this case, we had dou YC by dou AK of IJ. AK of IJ was activations, YC was some logit. Before we were backpropagating the logit directly, now we are taking a negative sign and backpropagating it. In other words, what is happening is you're asking the network to discount whatever it was seeing before. So you're asking the network to discount those regions that are making the prediction of YC. and you're looking at those the other regions that are present within the image in order to make a certain decision. So in this case, the other region is this kind of a cat image, or this kind of cat region. Again, the important part here is you're back propagating the negative of the logit rather than the logit directly. Any question here? So this is the counterfactual perspective. Next one is the contrastive perspective, which is YP rather than Q. So in this case, instead of backpropagating the logit, what you're backpropagating is a loss between the prediction P and some contrast Q. So if I want this to be between spoonbill and flamingo, then my prediction would have been a spoonbill, which is P, and my contrast would have been a flamingo. My prediction would have been a spoonbill P, my contrast would have been a flamingo, which is Q, and I'm going to backpropagate the loss between them. Let's say we had used cross entropy loss to train the neural network. I can use the same loss in order to backpropagate. You can use different losses, but for explanations have found that the cross entropy loss is usually the best, and you get these kind of different kind of explanations through it. And this is basically some kind of results that you can get out of it. I think again, this result is correct. I think there is a small here and a larger portion here. But the difference here is the loss between predicted class P and same class. Wait, I think I went to the next one. Yes. So this is the correct one. So loss between predicted class P and some contrast class Q is essentially what we are backpropagating. Again, the trainings is the same, the data set we used is the same, the network is the same. It's just that what we are backpropagating it is giving us this kind of different heat maps. Any question here? Yes. Yes, I would expect the same thing to be here. And that makes sense because you, again, going back to the question that you had before, given, let's say I have like 10 pixels that are causal to why this was a bull mastiff. If you're asking why bull mastiff rather than blue jay, the difference between these two classes is so different that you don't need to have a specific difference in order to say it's a bull mastiff. Just by looking at it, you know it's a bull mastiff. You don't really need to have a good explanation as to why these two are different. So I would expect the exact same thing that had in GradCamp to be the answer to this question. And there is a little bit of theory that goes into why that is the case, because think of Q. In this case, the probability of Q is almost zero, right? The Y blue jay is almost zero in this case. So when you backpropagate P and Q in that case, it's going to be almost same, and you're backpropagating that. So technically, it makes sense to have the same explanation. So in this particular method, you are constrained by P. P is already given to you by the network. You cannot change the prediction itself, unfortunately, right? So you're passing the network image through the network, you get a prediction already. And based on that prediction, we are taking a loss function out of it. So you're constrained on what P you already have. You just have a lot of latitude in choosing what Q you have in order to find the or ask for the explanation. Yeah. If there is a method that does that, yes, it will be overlap identical there as well. Yeah, if the prediction is wrong. Yeah. So the way you can actually do that is you add noise into the image itself, and you can add noise. So there's this entire field called adversarial image generation, where with a very small input, so you can't even see it, it's imperceptible. Noise you add to the image, it'll classify completely incorrectly. So you can add that noise, pass it through the image, and it'll give you a turtle. So if you want it to be a turtle, it'll give you a turtle. And based on that, you can make this kind of an explanation. But then that's a little bit more involved kind of thing. It requires an analysis of the noise, which is the adversarial image. And then there's the added context Q into it. So to analyze it, we need to have multiple levels of thinking about what we have done in order to get to this stage. But yes, but I would expect that there wouldn't be too much difference between them. Yeah. Oh, really? Okay. Oh, okay. Oh, okay. So that's actually very similar then. This is exactly what you do in adversarial image generation. Take JPQ, backpropagate it, and the loss or the noise at the, now we are taking the gradients in the middle layer, but if you take the gradients in the initial first layer, that is basically your adversarial noise. And you can add that back and pass it through and see what results you can get out of it. There's a ton of ways that you can think of changing stuff in order to get different things. I can even ask other kind of questions like why P rather than T. Now, it might not make just the question itself might not make too much sense, but essentially it's asking the question of why not bull mastiff with 100% confidence. So this essentially is telling us that, okay, you're telling me it's a bull mastiff, but you're only telling me with 70% confidence. What is preventing you from making this assertion with 100% confidence? So that is the why not bull mastiff with 100% confidence case. And the way we do it is loss between P and P, P and same class P. So in this case, Q is actually going to be P, where, and you can think of this as what you would do during training. So given a network, given an image, you backpropagate the ground truth backwards, right? So when you backpropagate the ground truth backwards, you're making small changes within the network, even though you don't think you're doing it because it predicted correctly, you're still making some changes. And that change is being reflected in this heat map. And it kind of makes sense here. It's not with 100% confidence because of the jowls here. So there is a small possibility that it might be a boxer, but the fact that the cat here exists makes you makes the network think that it's not with 100% confidence. It cannot say it. It's just saying with a certain amount of confidence that it is a bull master. Does this make sense? All right, so let's start looking at more kind of involved things for us to understand. So this now, we just looked at the method of generating it, but the analysis by itself is can be very involved. You can do a lot of analysis through this. So the first one is the spoonbill. We have the cat dog image, basically a no left image, and then a Bugatti convertible. So we're going to analyze on these four images. We're going to analyze a grad cam and some kind of contrastive explanations on top of it. So given this grad cam image, so given this image of a spoonbill, we pass it through grad cam, we get, and we contrast it against something like a flamingo, and this is the result that we get out of it. Again, the difference is in the leg, the shape of the leg and shape of the neck is essentially what you want the explanation to show us. But a neural network is not very well trained, so it's not able to see that the difference. Maybe I shouldn't say it's not very well trained. It's that it thinks the hierarchy of importance in the features is neck. So as soon as it sees that the neck is not as shaped, it doesn't care about what the shape of the leg is. As soon as it sees that the neck is different, it's just going to say, okay, this is why it is not different, which is, if you think about it, it's fine. It's kind of good that it knows this kind of feature importance or hierarchy as well without us saying it. Now, if you have some other thing like a pig, for instance, I think we showed fox before, then everything is different here. Now, why not spoonbill with 100% confidence? Well, the fact that there is this reflection at the bottom here is making sure that the network is kind of not sure of why this would be a spoonbill, or why it's not spoonbill with 100% confidence, because it's really not sure what to make of the bottom reflection in this particular case. We can actually do this thing for all these images, and you can see that many of these things are human interpretable, or in other words, what I mean by human interpretable is we understand it. Once we see the explanation, we can actually say that, okay, this is the reason why this particular explanation was made. There are some things that are exactly the same as GradCam. So Blue Jay image, why bull mastiff rather than blue jay in this particular case was exactly the same as GradCam, because as we were talking about before, the difference between these two classes is so large that you don't really need a explanation in this case. The face of the dog is so different from the face of a blue jay that just the fact that you're kind of highlighting is sufficient to know that it's not a blue jay, rather it is bull mastiff in this particular case. Now, there are some things that are non-human interpretable, or in other words, we need to have more of an involved discussion as to what this is. So for instance, let's take this stop sign, this image here on the stop sign. Let's say we start off with a no left image. Network is gonna tell us no left correctly. Now I'm gonna ask, okay, why no left? And that is where this solution comes into picture. It's no left because of this line that goes across the image, which is perfect, which is exactly what we want to see as well. And if I ask, okay, why no left rather than no right, it's actually showing the fact that there is nothing here. For no right, you would have expected an arrow to go in the opposite direction. So you would have expected a part of the arrow being in this part here. So this part makes sense. We can see it. Next one is if I'm given a stop sign and asked, okay, why no left rather than stop sign? A network, this particular contrastive explanation is showing us the bottom left corner. Now, human beings would look at it and say that it's not a stop sign because the letters S, T, O, and P are not in this image of no left sign, right? These STOP is not there. It's not written in the middle of the sign. But network is not showing that. A network is showing the bottom left corner of this particular image. So when we first look at this, it doesn't make too much sense to us. We shouldn't expect this to be the answer. This shouldn't be the reason why it's no left rather than stop sign. It becomes a little bit more clearer once we start understanding the training set, the network a little bit. So the network was trained on these 14 different traffic signs. So this is the entirety of what the network was trained on, just on these kind of traffic signs. Now, the most important thing here is to know is that stop sign is the only one with this kind of an octagonal shape. And there's this bottom left corner, there's this straight line. This kind of a straight line does not exist in this kind of a straight line, the bottom left, does not exist in any other image. So the fact that that left line is not there in the image is sufficient for the network to say that this image now belongs to, is not a stop sign. So a network has learned correctly. It has learned that, this is no left and this is stop, but it has taken the easiest way out. Neural network is as lazy as it can get. It basically finds the simplest explanation or simplest features that are different between two classes and tries to make an analysis. In other words, what I'm trying to say here is that the causal reason for why it's class A versus class B is not being found by a neural network. Rather, it's like basically water that is going downhill, right? It's just finding the easiest path downwards, and the easiest path in this particular case is this idea of straight line at the bottom left. So if I were to go back and show this image before, you would say that based on the GradCam image, there's no bias, it's all good, it's doing well. But then when we show the contrastive explanation and see the bottom left corner is when you start seeing the bias. That, okay, the problem is with the training data that we have had, where there was no other traffic sign with this bottom left corner. So it's not able to find, or it has not found out what the causal reason for either a stop sign is or for a no left sign. Right. So this is a way of further analysis where just simple questions like why P is insufficient to basically understand whether a neural network is working or not. You need to actually be able to go down a little bit further to have more kind of bias analyses, basically, to see whether a network is correctly working or it's incorrect. Yes. So yeah, something like that. Yes, exactly. Yeah. And the reverse is true as well. So if you were to construct a octagonal sign, but without stop in the middle and say that this is like a different class, then a neural network would learn that it's not just the octagonal sign, but something else is different between the two. Maybe that is the STOP basically. So yeah, it works both ways in that case. Any questions? Next, we'll move on to how to evaluate these explanations. So before that, if anybody has any questions about everything we talked about, which is all the direct explanations and these kind of targeted explanations, which are counterfactual and contrastive explanations. Again, everything that we did last week was more from a debugging perspective. Like if you're trying to debug your network, this is what you would do, first layer, last layer, middle layer, and all those kind of things. But from the intervention, GradCam and these contrastive, we have kind of expanded it and tried to look at it more from a question-based perspective. And this question is giving the context. The knowledge of human beings who are asking these questions are reflected within these questions, and that is where the context comes from. So you can use it for debugging, but more importantly, you can use it to answer or basically to explain to people who do not understand what a neural network is, and not just understand, but don't know the inner workings of the neural network. So that is basically what we'll be discussing today, what we discussed today, actually. So from this point onwards, it's about explanatory evaluation. So I just want to, till now, again, the way we have done it is just put 2-3 explanations next to each other and said, okay, which is better than the other. And it was very subjective. Some of you may have chosen one thing, others would have chosen another thing, and so on. It's on the person who's looking at it to decide if this explanation is good or not. But at the end of the day, the scientific method, it wants us to evaluate something objectively. And that is essentially what we'll be looking at right now. And we'll start off, and yeah, exactly. So this is from the last lecture and from this lecture, it's about these kind of evaluating explanations, and it was very subjective. We want to make it as objective as possible. Let's start off with looking at taxonomy of what how explanations can be evaluated. So we can think of three large portions, or three taxonomies in this case. Let's call it as human evaluation, application evaluation, and network evaluation. Now, the differences here are probably very important, and that's where the concept lies. Human evaluation is very simple. It's very similar to what we just did, which is human beings are going to look at these explanations and are going to directly evaluate explanations. They're going to say, let's say GradCam is better than guided backpropagation, or that vanilla backpropagation is better than GradCam. They make these kind of assertions by looking at the images directly. And the goal in human evaluation is for us to actually try to bring a certain level of objectivity to it, to these kind of subjective evaluations. We'll talk about how we can objectify these kind of human evaluations. Application evaluation, on the other hand, tries to find these tasks or applications where you have humans in the loop, but humans are not directly looking at the explanations. Rather, they have already looked at the data and made some kind of decisions, and our explanations are trying to reflect what that or reflect the regions that were used by humans to make those kind of decisions. We'll go through a little bit more in detail about two applications that can be used here, but essentially the goal here is to find what these applications are. The last one is network evaluation. Now, it's very difficult to have humans actually do the evaluation unless the person is looking to trust the system. If we are looking at large scale systems with like hundreds of thousands and millions of images, it's almost impossible for us to look through all these images, look through the explanations, the contrastive explanations, and make sense. So we're going to be removing the entirety of humans away from the last one, which is the network evaluation. And we're going to try to find these applications where we can evaluate the network based on the applications and say that it's indirectly related to explanations. Noise robustness is maybe one example of that. So let's start with the first one, which is the human evaluation. Again, this is one slide that we had shown last time, which is humans are directly asked to evaluate explanatory techniques. And the question is, which of these three techniques is better? So you can look at the left-hand side, which is vanilla backpropagation. The middle one here is deconvolution backpropagation. And the last one is guided backpropagation. All three are answering the question of why cat. If you remember the image that we had last week, it was a small cat in the middle. And this is basically showing us what this cat, the explanation for this particular cat. So you have these three things. And the question is, which of these three techniques is better? Now, the reason that human evaluation directly is not very good is because of this. It's very subjective. So, which is more important to us? Is it cleaner explanation, or is it class discriminative explanation? Or Another question you can ask yourself is, should it highlight the whole cat or only face of the cat? So if I look at the guided backpropagation, just the face of the cat is very nicely highlighted. The eyes, you can see everything within the face, but it's only the face of the cat that is highlighted. It's not the entirety, the other parts of the cat. So now the question is going to be, is this sufficient in order to make it a good explanation? And usually deconvolution explanation gives a more cleaner explanation, but I'm not really sure if this image is actually making that case. But essentially, what is more important? Is a cleaner explanation or some kind of a class discriminative explanation? Again, this is what makes this human evaluation very, very subjective. Um, how do we overcome this subjectivity? Well, as any other thing, we basically ask a large number of humans the same question. This is the motivation is taken from democracy, essentially. Large number of people ask the same question. Let's see what they answer. Hopefully they answer the same thing, or then we choose if not, then we choose the majority of those answers as the final answer of what is correct. So we have to ask a large number of humans basically to evaluate these explanations and make sure that the humans are unaware of the goal of the researchers. Like if I would have, let's say I am the author of, I've made a new technique called guided backpropagation. And if I've told you that I've done guided backpropagation, and if I'm telling you that, okay, yeah, choose among the three of them, and I'll also be I don't know, grading your papers or something like that, you will obviously hopefully choose guided backpropagation in that particular case. The reason being that, I've explicitly said that I'm the person who has made this technique. So it's very important that the humans who are looking at these explanations are not aware of the goal of or the intent of researchers. We also need to guide them through with questions. Like we have to make sure that they are understanding every small detail that is happening within the explanations. So generally, the way this is done is by using leveraging these large platforms. In this case, Amazon Mechanical Turk. I'm not sure if how many of you have, if you have heard of it or used it yourself, but it's essentially this huge platform where you can upload multiple images, videos, whatever you want to do, and ask human beings to label them essentially. So this is basically what the authors from GradCamp paper did. They took their method, which is here on the right hand side, and they compared it against guided backpropagation. So they uploaded the original image, this input image of this input image here, and then basically said that the left hand side is from robot A, right hand side is from robot B. It's actually from the same network. The same network is looking at them and giving you some kind of a result, but it doesn't matter. They're calling it robot A, robot B, because it's based on the method. One was GradCam, which is on the right-hand side, and guided backpropagation, which is on the left-hand side. And now the people were asked these following questions. Which robot is more reasonable? So the answer is person for both of them, but the question now is which explanation is better, is framed as which robot is more reasonable. Robot A seems clearly more reasonable than B. You have these 5 questions, and people were asked basically to choose one of these solutions. So so basically you're trying to remove the subjectivity out of it by making this comparison. And saying, okay, one is more reasonable than the other. You're not directly asked which is class discriminative, but you're asked what explanation is more reasonable. Now, you have to do it for multiple human beings, right? So 43 AMT workers, Amazon Mechanical Turk workers, were basically shown these kind of image pairs and asked questions. So 90 of these image question pairs were shown to people and they were asked. And so essentially, how many questions? 43 multiplied by 90 was the total number of opinions or opinions that we asked. And these people basically said in more than 80% of the cases, people chose GradCam as better than guided backpropagation. Hence, GradCam is better than guided backpropagation was how they basically wrote their paper and said that this is how we have evaluated it. Any questions in this case? This is just leveraging large human population and the access to technology to essentially show or to evaluate these kind of explanations. So the pro of these kind of human evaluation techniques is that it's based on answers from directly from humans. We are catering to humans. So now we are asking humans and asking them questions and hopefully getting answers from them and using them as a direct evaluation. But still, it's very subjective, even with large number of human beings. The thing is, most of us are very similar to each other, and we look at what is aesthetically pleasing versus class discriminative to make these kind of answers. So there's going to be biased. These questions can be framed in a way where one will be biased. So it's very important to, if it slips through the review process, this paper is going to exist. So it's very important to kind of make sure that bias doesn't exist. And the last question I think is very important. How many answers are sufficient? Here it was just 43 people. Somebody can say that 43 people is very non-representative, and maybe it's only from a particular locality or a location. So this is not as diverse as we want it to be. It's not as the answers here themselves are insufficient. So it's very hard to say how many people have to be asked this question in order to make a very objective kind of an evaluation. And these three things are going to exist. These three cons of this method are going to exist throughout. So um, basically, this is why we have two other taxonomies. Ideally, you'll have human evaluation as well. And with that, you'll have some kind of an application or a network evaluation, which we'll discuss in a little bit as an auxiliary to this thing. Human evaluation, extremely important because it's the goal of explainability, but it cannot be unbiased. It's very hard to make it unbiased. So there will be other methods that we need to look at for evaluating our explanations. And this is where the application evaluation comes in. So to reduce bias within the questions themselves, humans are not directly asked to evaluate something. So the problem here becomes is there because if people are directly asked which explanation is better than the other, right? So can we have other applications where that question is minimized? So the goal is that human beings are still in the loop somewhere within the application, but they are not directly asked this question of which explanation is better than the other. So let's take an example in this particular case. Let's say this example of, we were talking about the traffic signs before, right? Some kind of a localization example. So let's say I'm given a traffic sign of an intersection, sorry, an image of an intersection, and human beings are asked to pick out what traffic sign there is. Let's say there is a stop sign in this large image with an intersection. So a human being has looked at it and have localized the bounding box of where this traffic sign is. This has already been done. Now what we do is we pass it through an neural network that is trained to detect traffic signs, and it says that there is a stop sign, and it gives us an explanation as to this is where it has localized the traffic sign to a particular spot. Now the goal for the explanation is to make sure that the bounding box that the human being has looked at is the same place where the explanation is now showing. So this is a different place, or this is a different way of evaluation itself, where you are retroactively trying to explain something rather than looking at which explanation is better than the other. So these are the kind of explanations which can exist in this application evaluation. We'll be discussing two of these things, which is gaze tracking and pointing game, are two applications that we will look at. So what is gaze tracking? This is a very nice application where basically you can track gaze of human beings and say that given a certain image, these are the most salient objects or salient parts of the image that human beings are going to look at. So given this image, most people looked at this tree, at the line of cars here, as well as the traffic sign that is here, right? So these are the important parts of the image, and this is where human beings have looked at. In other words, if there is some decision to be made within this image, it would be because human beings have looked at it, and it's usually at these cases. So this is the assumption that we are making, that the important parts of the image are the parts of the image that leads to a particular decision. In other words, I want to make sure that my explanation looks something like this, or has a large overlap with these particular regions, right? Is there any question here on what gaze tracking is? It's basically tracking human visual gaze with specific objective results, essentially. So ideally, what we want to do is, given this kind of a heat map, based on gazes. So a number of people have looked at it. I don't remember exactly in this case. This is MIT 1003 data set. So I think that means it has about 1,000 images. And I think that tracked around 9 to 10 people's gaze across every single image. And based on that, they've created a heat map. In other words, this is the region that most people have looked at. So this traffic sign here is what most people have looked at. So essentially what we want to do is have a neural network when it predicts something, it needs to be able to predict at this spot. And this is what I was talking about in terms of a stop sign of or a traffic sign before. Now you don't create explanations and ask people to compare between the two. People have already looked at it, and you need to make sure that the explanation is also looking at the same spot. So you want to have explanations that have here. So you'll use something like mean intersection over union, which is like this metric between the two explanations, and say that GradCam has a 90% overlap with this heat map versus guided back propagation has a 78% overlap. So in that case, 90% you're going to say has more overlap with gaze tracking. Hence, it is a better explanation. So in this case, humans are not being involved in the which is better, but rather there's an objective metric, which is mean intersection over union, and an actual number, which is 90 versus 78, which we can point to and say that, okay, this is a better metric, or this is a better explanation that more follows our gaze. Is that clear? Any question? All right. I think we had a paper, this was back in 2020, where we showed this for multiple things. So the good thing about this is that you can do it across a large number of images because human beings have already looked at it. And it's not, we don't need to create Mechanical Turk again to basically ask these questions. In order to make the data set itself, the ground truth, all these human beings have already looked at it. So we can look at 1,000 different images and try to find these metrics. Before in the Amazon Mechanical Turk, it was just 90 question answer pairs, right? 90 images. Now we can do it across all 1,000 images and say that one explanation is better than the other. And you can have, I use mean intersection over union as one example as a metric, but there's so many other metrics. NSS is a metric, correlation coefficient is a metric. There can be a number of different metrics that we can now use to see what overlaps the other in order to say one method is better than the other. So GradCam, guided back propagation, there was another method, implicit saliency, and we can say that the implicit saliency is better than the other ones because it has a larger kind of an overlap with existing saliency metrics. So this is another way of trying to compare between different explanation methods. So there's no question about the saliency or gaze tracking itself. Another method is a pointing game. Now, the problem with the gaze tracking was that we were not given a directive. The way gaze tracking works is people are given an image and they're asked to just see the image. That's it. And then their eyes are tracked. So there's no way for us to create a supervised kind of contextual questions and ask why P rather than Q, why, what if, and these kind of other questions. So in this case, what we need to do is have a different kind of a method where, and this method is called pointing game, where pointing game is you're given an image, but the image is blurred and you're kind of asked a question. So given a blurry image and a questions, humans are asked to sharpen the regions in the image that lead to their decision. So this particular image, I think it's playing some game, volleyball or something like that. And people are asked, okay, what makes you think that this is based on a game? And human beings need to kind of de-blur the regions or within the image, which leads to their answer. So this is pointing game. So here in this case, you're not actually, there's no thing where they're tracking the gazes, rather just given a screen and a mouse where, when you click on something, something is de-blurred. Essentially, you can have these kind of answers to this question of pointing game. So based on pointing game, we can have these kind of heat maps again. These are the regions. So given what color is the hydrant and the answer is red, the people, in order to make this decision, kind of de-blurred this part in order to say that the answer is red. Same thing here as well. What color are the animal's eyes? Green, and they de-blurred this part of the image. So essentially, it's similar to the gaze tracking, where we are getting the heat map, except that now it's based on this kind of a supervised question that we can ask the human beings, and they would have answered in this particular way. So um, we can do the exact same thing as before. We can say, okay, algorithm A is giving us a better result compared to algorithm B because there's a higher overlap between the mean intersection over union or the correlation coefficient or NSS or any of these metrics, and say algorithm A or explanation A is better than B in this particular application. Any question about the two applications? Mhm. Yeah, you can do that for sure. But again, the question then goes back to what is an explanation? Is it a justification of what the network has done versus is it something that is helping to improve the network later on? Now, if you have used this kind of metadata in order to train the network, then it is biased in the sense that its explanations are going to be based on what it has already trained, correct? So in that case, yes, your explanations are definitely going to be better. But then the question becomes, what are you going to be using these explanations for? If it is to evaluate the network, then it's biased. But if it is to in a machine teaching setting where you're teaching someone what is the what is the spoon bill, for instance, in that case, yes, it is definitely going to be better in that case. So it then comes down to what is the reason that you want an explanation in the first place. So there's some good things about this kind of application evaluation, which is that you are removing the bias with humans when it comes to which one is better than the other. The subjectivity is being removed, but you're adding a different kind of a problem, which is that each application, the way you want to interpret your explanation is going to be different. Now, gaze tracking, for instance, it would have required expensive eye tracking equipment, but more importantly, it may lead to kind of spurious noise and center bias. As a human being, we are always trained to look at the center of where we are looking at our field of view, and that basically is center bias. So if your traffic sign or whatever we were looking at before is not in the center, it's off to the side, there will be some spurious correlations in the middle because that is what we'll look at in the beginning. We look at it and then we'll move on to that part of the image which is the most surprising or the most salient for us. So there's going to be a lot of spurious noise. Again, we talked about no targeted explanations or questions can be asked. So this is very hard, right? So it's impossible to have some kind of a targeted answer or explanation in this case. Now, this kind of stops in the pointing game. In the pointing game part of it, we can ask these kind of questions and then ask to deblur images. But targeted questions, answers and explanations can be obtained based on targeted questions in this case, but you can see that it's a very contrived kind of an application. It is very hard to say that if it does well in this particular application, the explanation has worked because the entirety of the way we have designed this application almost seems like we are doing it for the application of explanation. So it's very hard in this particular case to justify this idea of application evaluation for this application. So sometimes while it is good to do this kind of application evaluation, we have to be very mindful of the type of application that we are using in this case. Any questions before we move on to the last one, which is network evaluation? If not, then this is just one slide because this is a very, very large topic. Yes. Different answers, yes. So gaze tracking is done on like 50 different people. I forget how much it was done here. I don't think it was 50. I think it was much lesser, but there are newer data sets which has a lot of people. So once you have, let's say, 50 different things here, you kind of overlap one on top of the other. And you have this as a heat map that is from multiple things. Same thing with the pointing deblurring thing as well, where you have for multiple people, you get this kind of a heat map. Yeah, I think so. Yeah, the blue is just one person. This person has looked here, 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 maybe here, here, and these kind of things. So the color coding here is number of people. So the last one, which is network evaluation, it's a very, very large kind of application. We're not going to cover that at all because it doesn't involve human beings. The evaluation does not involve human beings. You're making this kind of an assumption that the most explainable neural network is the one that has learned the actual causal features, which is not always true. It requires this idea of causal emergence within the neural network, which again is not always true. So we're going to be ignoring or not talk too much about this, but there is a large set of applications like robust classification, anomaly detection, which I think will be a lecture in the future, machine teaching, there's something called active learning. All of these things, if your network is doing good in these other auxiliary applications, then that means a network is more explainable, is basically the idea. There's a very large set of these applications. There's this paper called Towards a Rigorous Science of Interpretable Machine Learning, which covers a taxonomy in this particular case, which talks about all these kind of applications of network evaluation. But essentially, this is if you look at the newer papers, if you look at the explainability papers from the, I think it started around 2013 for these neural networks. It started off with human evaluation. It moved on to application evaluation. These days, most works that come out have this idea of robustness. So any explainable network needs to be very robust is some kind of an assumption that we have made, and that kind of empirically kind of works. If you want more explanations about basically what we covered for this, we did too many things actually, quite a lot of stuff: explanatory paradigms, reasoning, RADCAM, contrast, counterfactual, and this entire idea of explanatory evaluation. So there are multiple papers that have been listed here that you can actually go through and try to read through. But that is essentially the end of this lecture. If anybody has any questions, we can stick around. Otherwise, thank you.
So, please find your name on the paper. Thank you so much, Moin.